Welcome back to The Explainer. Today, we're tackling a massive, honestly, pretty technical challenge in modern grid automation. We're talking about managing geographically dispersed, utility-scale battery energy storage system fleets, or BES fleets for short. Now, as our power grids evolve and we start relying heavily on renewable energy, making sure these massive battery fleets respond perfectly, that's absolutely critical. But as we're going to see, the technology we've been relying on to manage them might actually be fundamentally mismatched for the job.
Okay, let's dive into this. We've got a clear roadmap today. We'll start with Section 1, the Cloud SCADA standard, then hit Section 2, the latency bottleneck. From there, Section 3 covers dangerous operational blind spots. Section 4 brings in the edge computing solution, and finally, Section 5 is all about balancing cloud and edge. Let's get right into it.
Section 1. The Cloud SCADA Standard, Managing Geographically Dispersed Assets.
So just to establish a baseline, let's look at how things are set up right now. Fleet operators managing these geographically dispersed utility-scale storage assets usually rely on fragmented cloud-hosted SCADA platforms. And, it makes sense, right? They need to maintain visibility over assets that might literally be spread out across hundreds of miles. For asset performance managers, centralized cloud platforms are the go-to standard just to keep an eye on everything from one single place. It gives them centralized fleet visibility. But here's the catch. While seeing your assets is great, controlling them during a grid emergency is an entirely different beast.
Section 2, the latency bottleneck, when milliseconds matter. Right, here is where the physical reality of grid instability literally collides with our network architecture. We really need to talk about fast frequency response events. These are sudden, totally unpredictable dynamic shifts in the grid that demand an immediate, millisecond-level ancillary response from our storage assets. When the grid's frequency suddenly drops or spikes, multi-megawatt batteries have to react instantly. It's like pulling your hand away from a hot stove. If you had to send an email to your brain to get permission first, you'd get burned, right? We are not talking about minutes or even seconds here. We are talking about milliseconds. That speed is completely non-negotiable.
And this brilliantly illustrates the core conflict we're dealing with. On one side, we've got the physical grid demanding millisecond-level dynamic responses, but on the other side, we have high-latency cloud architecture trying to manage it. I'm sure you see the problem here. Relying purely on a system where data has to travel from a local inverter all the way up to a centralized cloud server, get processed, and then travel all the way back down, well, it introduces massive critical vulnerabilities. It's just a fundamental mismatch in speed.
Section 3. Dangerous operational blind spots. Breaking the communication loop.
Let's zoom in on exactly where and how this system breaks down. The main issue is right there in the communication loop between the centralized energy management system, the EMS, and the local inverter controls. And there are two big technical culprits causing delayed commands. First up, network jitter. Just the natural, everyday fluctuations in internet transmission speeds can add fatal milliseconds. And second, API bottlenecks. When those central servers try talking to local controls, the software interfaces themselves can get jammed up, severely slowing down the dispatch of critical commands.
So what exactly happens when network jitter and API bottlenecks delay those commands? Well, the result is that command delays create dangerous operational blind spots during fast-frequency response events. Think about the real-world stakes for a second. We're dealing with multi-megawatt assets, massive batteries capable of dumping or absorbing huge amounts of power onto the grid, and they're essentially flying blind precisely when we need them the most. The centralized system might know exactly what needs to happen, but it just can't get the command to the asset in time.
Section 4. The edge computing solution. Localizing intelligent decision-making. Let's move to and see how this builds, because thankfully, there is a real structural fix to this fatal latency flaw. We don't have to keep flying blind, but we do need a massive paradigm shift in our architecture. Step 1. We absolutely must push intelligent decision-making down from central servers to the edge of the network, meaning right at the physical site of the batteries. And Step 2. That decision-making has to be executed via local deterministic controllers. We literally have to stop waiting for the cloud to tell the asset what to do in a split-second emergency.
By putting that intelligence right at the edge, local controllers can handle real-time dispatch and protection routines completely autonomously. Think about it. By operating autonomously with deterministic control strategies, meaning they follow very strict pre-programmed rules without asking for outside permission, we entirely wipe out the communication latency and API bottlenecks we just talked about. The local system detects the grid shift and responds in milliseconds, all on its own, without waiting for that round-trip ticket to a centralized cloud server.
Section 5.
Balancing cloud and edge, the new division of labor.
Now, what's really interesting about this slide is how it all comes together. Does this mean we just toss the cloud in the trash? Absolutely not. We just need to reassign roles to create a really optimized division of labor. We reserve the edge strictly for those ultra-fast, mission-critical tasks, real-time dispatch and autonomous protection routines. But the cloud remains incredibly valuable. We leave the cloud for what it does best: telemetry, gathering long-term analytics, and non-critical reporting. It's all about using the right architectural tool for the right job.
To perfectly sum up the core vulnerability we've explored today, we really have to acknowledge a simple truth straight from our source material. Cloud latency simply cannot match the physical realities of grid instability. It really is that simple, and frankly, that stark. You cannot fight physics with a slow internet connection. When the grid shifts, the response has got to be localized, instantaneous, and completely deterministic.
So, I want to leave you with a direct challenge today, especially for the software architects and asset performance managers watching this explainer right now. How is your fleet balancing centralized cloud visibility with ultra-low latency edge execution? Are your multi-megawatt assets relying on a slow round trip to the cloud to protect the grid? It's a massive, critical question that demands a real evaluation of your own systems if we're going to build a truly resilient, automated energy grid. Thanks so much for joining me for this explainer, and I really hope it gave you some powerful structural insights to take back to your teams.